We often imagine science as a steady march forward, each discovery neatly building on the last, but the history of science tells a far more dramatic story. At pivotal moments, entire ways of seeing the world have collapsed and been replaced by new frameworks that reshaped what scientists believed was real, knowable, and even worth asking about. In this video, we'll trace 20 major scientific revolutions, moving roughly chronologically from the Renaissance to the present, to see how these paradigm shifts transformed astronomy, physics, chemistry, biology, medicine, and beyond. What emerges is not just a history of breakthroughs, but a deeper pattern. Science advances by periodically reinventing its own foundations, and with them, our understanding of nature and ourselves. 20 major scientific revolutions ordered roughly chronologically. Each represents not just a discovery, but a paradigm shift, a transformation in how nature itself was understood, what counted as a legitimate question, and what methods were considered authoritative. 1. The Copernican Revolution, 1543. De Revolutionibus Orbium Coelestium, published in 1543, Copernicus's work displaced Earth from the center of the cosmos and replaced the Ptolemaic geocentric system with a heliocentric one. This was not merely an astronomical correction, but a profound conceptual upheaval. Motion, observation, and cosmic order had to be rethought from a sun-centered perspective. The change challenged Aristotelian physics, theological assumptions, and the reliability of common sense, initiating a centuries-long transformation in humanity's self-understanding and laying the groundwork for modern science. The Galilean Experimental Revolution, 1610 to 1638. Galileo Galilei. Through telescopic discoveries, 1610, and systematic experimentation culminating in discourses, 1638, Galileo replaced qualitative, authority-based natural philosophy with quantitative, experimental science. He redefined nature as something that could be measured, mathematized, and tested, not merely interpreted through inherited texts. This revolution established experimentation and mathematical description as the gold standard of physical knowledge, reshaping how truth in science was justified. 3. Newtonian Classical Mechanics, 1687. Philosophia Naturalis Principia Mathematica, published in 1687, Newton's Principia unified terrestrial and celestial motion under universal laws of motion and gravitation. The paradigm shifted from fragmented explanations to a coherent, predictive mathematical system governing all physical bodies. Nature came to be seen as a deterministic machine operating according to universal laws, a worldview that dominated physics for over 2 centuries and deeply influenced Enlightenment philosophy. The Chemical Revolution, 1789. Traité élémentaire de chimie, with the publication of his elementary treatise on chemistry in 1789, Lavoisier overthrew the phlogiston theory and replaced it with a new paradigm based on oxygen, conservation of mass, and systematic nomenclature. Chemistry was transformed from a qualitative art into a quantitative science grounded in measurement and clear definitions. This revolution redefined what substances were and how chemical reactions were understood. Atomic Theory, 1808, a new system of chemical philosophy. John Dalton's 1808 work proposed that matter consists of discrete atoms combining in fixed ratios, fundamentally altering chemical explanation. Chemical laws were no longer empirical regularities alone, but reflections of underlying atomic structure. This paradigm provided a theoretical foundation that unified chemistry and enabled later advances in molecular science. 6. Electromagnetism, 1864. James Clerk Maxwell. Maxwell's equations, completed in 1864, unified electricity, magnetism, and light into a single theoretical framework. Fields replaced particles as fundamental explanatory entities, and light was revealed to be an electromagnetic wave. This revolution reshaped physics's ontology and directly paved the way for relativity and modern field theory. 7. Thermodynamics and Entropy, 1850-1877. Ludwig Boltzmann. The development of thermodynamics and statistical mechanics, culminating in Boltzmann's work in the late 19th century, introduced entropy and irreversibility into physics. Nature was no longer fully reversible or perfectly ordered. Probability and disorder became fundamental. This paradigm shift altered how time, energy, and physical processes were understood. 8. Darwinian Evolution, 1859. On the Origin of Species. Published in 1859, Darwin's theory of natural selection replaced static species with populations shaped by variation and selection over deep time. Biology shifted from a taxonomy of fixed forms to a historical science explaining adaptation and diversity. The paradigm reframed life itself as dynamic, contingent, and law-governed without requiring teleology. 9. Germ theory of disease, 1860s, 1880s. Louis Pasteur. Pasteur and others demonstrated that microorganisms cause disease, overturning miasma theories and redefining medicine. Disease became a biological process with specific causal agents rather than an imbalance or environmental vapor. This revolution transformed medical practice, public health, and experimental biology. In the first half of this series, we saw science break away from ancient authority and discover the power of laws, experiments, and mathematical order. But the revolutions we're about to explore go even further. They don't just refine that framework. They strain it, fracture it, and in some cases, overturn it entirely. Beginning in the late 19th century, science starts to confront limits of certainty, limits of observation, limits of reductionism itself. From the hidden order of the periodic table to the collapse of absolute space and time, from probabilistic particles to an expanding universe with a beginning, these revolutions force science to rethink not only what the world is made of, but how it can be known at all. We trace the next 10 scientific revolutions, moments when structure emerged from chaos, information rivaled matter as a fundamental concept, and science increasingly turned its gaze toward complexity, systems, and even its own methods of knowing. 10. The Periodic Table, 1869. Dmitri Mendeleev. Mendeleev's table reorganized chemical elements into a predictive structure based on atomic properties. Chemistry gained a unifying framework that revealed hidden order and anticipated undiscovered elements. The paradigm shifted from cataloging substances to understanding systematic relationships. 11. Relativity, 1905 to 1915. Albert Einstein. Between 1905 and 1915, Einstein replaced Newtonian space and time with space-time, relativity, and gravity as geometry. Absolute simultaneity and fixed frames of reference were abandoned. This revolution redefined fundamental concepts of motion, mass, energy, and causality. 12. Quantum mechanics, 1925 to 1927. Quantum mechanics. Developed in the mid-1920s, quantum mechanics overturned classical determinism at microscopic scales. Probability, wave-particle duality, and observer-dependent measurement replaced classical trajectories. The paradigm forced physics to accept fundamental limits on knowledge itself. 13. The Big Bang cosmology, 1927 to 1965. Big Bang theory. Emerging from expanding universe models and confirmed by cosmic microwave background radiation in 1965, the Big Bang theory replaced an eternal, static cosmos with a dynamic, evolving universe. Cosmology became a historical science with a beginning in time. The universe itself acquired a developmental narrative. 14. Molecular biology and DNA, 1953. DNA double helix. The 1953 discovery of DNA's double helix structure revealed the physical basis of heredity. Biology shifted from descriptive study to information science, centered on coding, replication, and expression. Life became intelligible in molecular and computational terms. 15. Plate tectonics, 1960s. Plate tectonics. In the 1960s, continental drift, seafloor spreading, and mantle convection were unified into plate tectonics. Earth's surface was reinterpreted as dynamic rather than static. Geology became a coherent global science explaining earthquakes, mountains, and continents. 16. The Information Revolution in Science, 1948. Claude Shannon's 1948 theory of information redefined communication, noise, and signal in mathematical terms. Information became a quantifiable physical and conceptual entity. This paradigm reshaped computing, neuroscience, genetics, and systems science. Chaos theory, 1960s to 1980s. Chaos theory revealed that deterministic systems can exhibit unpredictable behavior due to sensitivity to initial conditions. Order and randomness were no longer opposites. This revolution altered modeling across physics, biology, meteorology, and economics. 18. The modern synthesis in biology, 1930s to 1940s. Modern synthesis. By integrating Mendelian genetics with Darwinian evolution, the modern synthesis unified heredity, variation, and selection. Evolution became mathematically and experimentally grounded. Biology gained a coherent theoretical backbone comparable to physics. 19. Systems biology, 1990s to 2000s. Systems biology shifted focus from isolated genes to networks, feedback loops, and emergent behavior. Living organisms came to be understood as dynamic systems rather than linear pathways. This revolution reintroduced holism within a rigorous quantitative framework. 20. Artificial intelligence and data-driven science, 2010s present. Artificial intelligence, machine learning, and AI transformed scientific practice by enabling pattern discovery without explicit mechanistic models. Prediction sometimes precedes explanation. This emerging paradigm challenges traditional notions of theory, causation, and understanding itself. Taken together, these revolutions reveal a striking pattern. Science does not simply accumulate facts about a fixed world, it repeatedly reconstructs the very framework through which the world is seen. Each paradigm shift redefined what counted as evidence, explanation, and even reality itself, often overturning ideas that once seemed unquestionable. From a sun-centered cosmos to probabilistic particles, from static continents to living information systems, scientific progress has been less a straight line than a series of deep reorientations of human understanding. Seen through this lens, the history of science is not just a record of discoveries, but a story of intellectual humility, a reminder that our most powerful theories are provisional, shaped by their time, and always open to transformation when the world demands a new way of seeing.